Thank you. So I'm going to talk about the geometry of some algebras related to the Weyl groupoid. So let's start. I'm going to assume that G is a classical simple Lie superalgebra with Cartan subalgebra H. And there are two algebras of interest. One is called I of H. It's a subring of the W invariants of the symmetric algebra. It's contained in S of H to a W, and it's the image of the injective Harish-Chandra map from the center of the enveloping algebra to I of H. And this algebra is the algebra of invariance for the action of the Weyl groupoid on S of H. There is another algebra which is also relevant. So here you take a Lie supergroup with Lie superalgebra small g, and then you look at the J of G, which is the reduced Grothendieck group of reduced Grothendieck ring of finite dimensional G modules. Okay, so mainly I will work with I of H, but the theory also applies to the complexification of J of G. Both are invariant rings for an action of the Weyl groupoid. So in what follows, A could be either of these algebras. And the main themes are, first of all, the North-Star-Ansatz, which gives you a one-to-one correspondence between radical ideals in A and their zero sets in H star, and I call these zero sets super algebraic sets. And secondly, the algebra I of H has the ascending chain condition on radical ideals. This means that any super algebraic set is uniquely a finite union of irreducible ones. And you don't need to know much about these superalgebras to understand this talk, because everything is defined in terms of some combinatorial data. So you have delta, a finite subset of H star. H star is a finite dimensional vector space, and delta is called the set of roots. And you have a non-degenerate symmetric bilinear form, which is invariant under the finite root W. And then you have some isotropic roots. These are all alpha in delta, such that alpha comma alpha is 0. And this should be non-empty. Well, the first part is just some basic ring theory. I'll assume that I have two commutative rings, A inside B, and T is an element of A, such that TB is contained in A. And then you see, if you have a radical ideal, P of A, that contains, where T is contained in P, then TB is contained inside P. And to prove it is one line. You take the square of TB, right? And now T times B is contained in A, and T is in P, so the square will be in P. If P is radical, then TB must be contained in P. And another remark is that if T is a non-zero divisor and you localize A at T, you get the same localization as B localized in T. And then it's well known that there's a bijection between primes in A that do not contain T and primes in the localization. And if you identify both sides of this equation star, then you are able to write spec A as a disjoint union of spec B sub T and the inverse image of C, where C is A over TB. All right. This just want to summarize again what I said. T is an element of A. A is a subring of B, such that TB is contained in A. Then you have this disjoint union of spectra, and this is what gives you a handle on prime ideals of A and on particular with maximal ideals of A. Now, the localization of A at T and B at T are the same, and B is finitely generated over the field. So we know what spec of BT looks like, and we need another ingredient to deal with spec of C. Oops. So let's explain first how this applies. The ring I of H is all invariant polynomials which are constant along certain hyperplanes. So if lambda is in pi alpha, and f of lambda is equal to f of lambda plus t alpha. And the previous results apply to A contained in B. A is I of H and B is S of H through W. And T is the product over all isotropic groups alpha of certain elements H alpha. And what these H alpha are, the bilinear form induces an isomorphism between H star and H, and H alpha is the image of alpha. Now, kind of by definition, T is the T vanishes on all the pi alpha, right? And so anything multiplied by T vanishes on pi alpha, and so in particular, they are constant along these hyperplanes. So maximal ideals of A that contain T are well known, and we need one more ingredient to study maximal ideals in the factor ring. And what we need is the Duflo gun of a functor. I won't say too much about this functor. It's a functor from G modules to GX modules. And so GX is a Lie superalgebra at a smaller rank than G. And this induces maps from I of H to H sub X, and J of G to J of G sub X. So it induces maps to similar algebras of smaller rank. And we can try to prove things by induction. So then you set up a commutative diagram where A is I of H and B is the symmetric polynomials, and AX and BX are similar algebras in smaller rank. And then we need to know what the kernel of small phi is and the image. And the kernel is just T times B, which is very good because it means that the image is A over T times B, and that's the algebra we're interested in. And the algebra is, well, sometimes the map phi is surjective, but at the worst, it's the image is a is the fixed ring under an automorphism of order 2. So, so using this, you can use induction and prove a result about maximal ideals, that the restriction maps from S of H to S of H to W and then to I of H. These restriction maps on maximal ideals are onto. And one corollary of this fact is that any central character of U of G is the central character afforded by a Verma module. Okay. And then we have so that was the weak Nullstellensatz. It tells you about maximal ideals, and the strong Nullstellensatz is the one which relates ideals to their zero locus. So if I is an ideal of I of H, we look at its zero locus, and that's all X in H star, where every polynomial in F vanishes, every polynomial F in the ideal I vanishes. And a set of this kind is called super algebraic. And then there's a bijection from radical ideals in A to super algebraic sets. Well, I just want to briefly tell you about actions of groupoids on varieties. So for variety X, A of X is the groupoid with objects all subvarieties of X and morphisms or isomorphisms between objects. And we'll say that the groupoid G acts on X if there's a functor from G to A of X. So then you can define orbits. Suppose that G is a groupoid that acts on X and X a point in big X. Then you can define an equivalence relation where X tilde Y means that there's some groupoid element that takes X to Y. And the equivalence classes are called orbits. So the groupoid does not act on the ring, but you can still define an invariant ring which consists of all functions that are constant on orbits. Now, unfortunately, the usual Weyl groupoid, for the usual Weyl groupoid, the orbits are not closed. And that is a bit of a problem. So we can fix it by introducing a continuous Weyl groupoid. So then it acts on a hyperplane pi sub alpha by translation in the direction of alpha. And the usual Weyl groupoid moves lambda to lambda plus n alpha. So you get a discrete non-closed orbit. If you have two orthogonal roots, then you can move lambda both in the direction of alpha and beta. Okay, I think this is the end. Here's what we can say about orbits. O lambda is the orbit of lambda. And then you take f of lambda to be a maximal set of mutually orthogonal isotropic roots, which are all orthogonal to lambda. Then O of lambda is a finite union over the Weyl group of something. And let's just look inside that union. And what you have then is an affine hyperplane, or rather affine subspace of H star. And well, in particular, all orbits are closed. And the dimension of O lambda is this number of elements in F lambda. And if M of lambda is the maximal ideal of SH corresponding to lambda, and small m lambda is its intersection with I of H, then the zero set of small n lambda is this orbit, and we get a bijection from maximal ideals in IH to WC orbits on H star. So I think that's it. Thank you very much.